Okay, morning. Today we would like to move to the chapter 7, and the topic is the energy equations. So, as we know, the energy equations can be applied to hydroelectric power generations, and the basic idea is satisfy the energy conservations. And there are many uh, topic we will focus on, uh, such as the pumps and the turbine. And since we introduce the energy equations, and we will also tell you what is the power equations. And the most important thing inferred from this chapter is the head laws. And this is we will introduce what is the head laws, and usually we use the parameter names is the HL. Okay, so here is the learning outcomes, and I just skip, and I would like to highlight the important topic will be presented in the end of this chapter is the EGL and HGL, which is widely used to describe the variations in pressure and velocity for the fluid flow field. So this is very, very important for our hydraulic problems. So I will take around 10 minutes to introduce the two parameters today. So this slide just summarize all units which are widely applied to the problems. So what is the work? And the work is also the indicated the energies. So this is the very normal unit for energies. We call that is power. That means the energy associated with a force of 1 Newton acting through a distance of 1 meter. And then another way to define a unit of energy is describe the heatings of waters. So we have the small car and the large car. The small calorie is equal to the energy required to increase temperature of 1 gram of water by 1 degree. And we know that actually 1 small calorie is equal to 4.187 hours. Large calorie is the amount of energy to rise 1 kilogram of water by 1 degree. And also, the PU is the amount of energy required to rise the temperature of 1 lpm of water by 1 degree F. So the two units of the energies, the first is joule and the second is calorie. So you need to keep in mind those important units shown here. And the slides just show there are 5 important energies: the mechanical, thermal, chemical, electrical, and the nuclear. So most of the problem we focus on the mechanical energies. The energy is directly associated with motions. Okay, so how can we compute the work? Since we know we have the external force acting on top of block, and the block is moving with a certain distance s, so we can directly multiply the force by the distance. This is for the situations when the block is moving with a straight line. But if our graph or our problem include rotational motions, so we need to apply the moment multiply the rotate angles to compute the work. And this work we call that is rotational work. And since we already compute the energy or the work and divided by the certain time intervals, we will have the powers. So usually we use the name is the rate of work. And then we if we the power can directly computed by the force multiply the moving velocities. And if our problem include the rotating problems, so the power is equal to the moment multiply the angular speed. And the pattern of this slide showing here, this is a very important dynamic transfers. We know that the 1 HP is horsepower is equal to the 746 watts. So we just highlight the unit for the power. Usually we use the watts and also the HP. And there is the relationship and the constant computed factors for the watts and the HP. So, and as I mentioned for our first slide, there are two important topics. One is pump and another is turbine today. And usually we use the WP indicate the energies. The pump provide energy to a flowing fluid, and the turbine is extract energies from a flowing fluid. We use the WP. So those two parameters are very important and will be used today. So that's now we consider consistence, and we use this is the closest systems. So only have two ways to change the energies. The first one is the work, and the second one is the heat transfer. We use the W and the Q. And noted that the energies is a property of a system that the work W and the heat transfer Q are interactions that occur on system boundaries. So we know that the delta E, which is increase in energy stored in the systems, is equal to amount of energy that entered the system by heat transfers Q. And the minus, very important here is the minus amount of energy that left system due to work. So we have the work. So if you have the energy stored in the system delta E divided by the certain time intervals, the unit will change to the hours. So use the Q rate and the minus W rate here. So there are four sentences summarize the properties here. As I mentioned here, if the W is positive, so that means the work is positive here, but you just consider there is a negative sign here. So if the work is positive, and then we'll let the delta E decrease. So you see, if you notice that the sentence showing here, the work is done by the system on the surroundings. If the W is negative here, so if the work is done by the surroundings on the systems, So this is work is minus, and we have additional minus here. So we'll let the energy stored in the systems. So that's why there is the down by the surroundings on the system. So that the energy in the system is increasing. Okay, if you take a look, follow this equation, you can easily to figure out what are the positive and the negative meanings. Again, and then if the Q are positive, here will let the delta E increase. So if that's the case, if the heat is transferred into the system, so the energy increase. The minus here, so the energy will decrease because the transfer out of the systems. Okay, so that we notice that for our problems is based on the linear transport series, and now we are interested on the extensive property E is energy here. That means in case the intensive properties B is energy divided the mass, we use the small e here. So we know that actually the dE dt is equal to the Q rate minus W rate equal to the energy changes in the control volumes with the time, and then the energy changes, this is energy flow exchanges around the control surface. So what is the small e in here? It's the unit per mass in the fluid. So actually we know that the E include the kinematic energies, potential energies, and the final is internal energies. So kinematic energy we know that is well equal to the 2 over V squared. And the potential energy we know that is equal to the G gravity and multiplied elevations. And what is the internal energies such as the chemicals, electric, and the heat energies? We can rewrite the equations dE dt is equal to Q rate minus W rate and equal to the dt over the energies per unit mass in the control volumes and the energy rate exchange along the control surface. This is our equation 1. And we go details for the W rate. Actually, the W rate can be separated into the two items. The first is the shaft work. The second is the flow work. And we use the name is W shaft and the plus the W flow. So the W flow is quite easily associated with a pressure force. So in other words, the W shaft is any work that is not associated with a pressure force. So we first focus on these items, the work for the shaft. We have to count of the work related to the W shaft. So the one is the turbines, another is the pumps. As I mentioned, the W, if the W is the negative sign here, that means the pumps, the energy from the pumps uh, will provide into the systems. And if the W is positive, that means the work done by the turbines will out of the energy will out of the systems. So that's why here is W turbine minus the W pumps. And we focus on the second items for the W flow rate. So this is actually the work associated with a pressure force. So if we see this is a laminar flow, or no, that's really laminar flow, we just consider our flow condition is the pipe flow. And we have the cross section 1 and the cross section 2. Because it's an inner pipe, so we have the pressures at the cross section 1 and the cross section 2. And we actually know that the definitions of the work is the force acting with the certain distance. So we have the first two in here. What is the force 2? The force 2 is contributed from the pressure force, and we have the cross section area 2 here. And what is the delta X distance? Because we actually know that the flow with the V2 velocities and with the delta t time pass. So we know that the distance delta x2 here is the V2 velocity multiplied the delta t timings. So we know that the work of the two pulsation 2 is the P2 multiply the area 2, and we have the velocity and the multiply the delta t. But we would like to compute the rate of the power of the work, the powers. So finally, we only have the P2, A2, and the V2 velocities. And if we take a look, we know that the mass flow rate is equal to rho AV, right? So we just put the density here, and also divided the density outside, so we can have the mass rate parameters in here. So finally, we know that the W rate 2 is equal to the mass 2 rate, the P2 divided the rho. So similar to the W2 and the W1, we can rewrite it to the M rate, and we have the P1 and the rho. Then the actual difference here compared to the cross section 2, there is the minus, because as we know, the minus is the inflow cross section area. So that's why we use the minus, because the, the normal factor of the cross section area is opposite to the flow directions. So that's why there is the minus. And since we know the pipe flow is always satisfying the continuity equations, so actually the mass flow 1 is equal to the mass flow rate 2. And we just use this is the same mass flow parameter M rate. So we can rewrite the work flow rate is equal to the work flow rate 2 and the work flow rate 1. So the N rate P2 divided rho minus N rate P1 divided rho. And if we consider a situation involve multiple processing area, so there we will have the sum of the outflow and the inflow energy. So, but since we cannot actually know the flow directions is always parallel to the normal factor of the cross-section area. So we involved the dot years, and we know that there's an outflow minus the inflow. We can deal the problem with the integrations along the control surface. So finally, we know that the work rate include the shaft work rate and the flow work rate, and the shaft flow work rate is equal to the turbines minus the W pumps plus the control service integrations of the energy flow rate. So this is our equation 2. So if we put the equation 1 and the equation 2 together, you know that we can put the stage equation 2 go back to here. Okay, so we can rewrite the equation 1 be the Q rate minus WT rate plus the WG rate and then minus the integration along the control service, the P divided rho and the rho V dot dA. And the right hand side is right by based on the based on the neural transport theory to just replace the small b by the energy items per mass unit. So we just take a look. There are two integrations along the same domains, the control service. So we just put two items together. So the right hand side here we have additional pressure items here. So this equation is our equation 3, and then if we just replace the item, the pressure divided the rho plus the internal energies, we call that is the specific entropy H. And this is a very famous parameters be used in the thermodynamics problems. But in our chapters, we don't use that, so we just take a look and keep in mind. So we still stop in the equation 3 here. So if we consider the equation 3, we take a look, that's a little bit difficult to deal with the problem for the integrations, because you see there is a v square and there is the v outside. So the problem to deal with the integrations is too complicated for these items. So this chapter just proposes use the kinematic energies correction factor alphas. The purpose why we need to have the alpha correction factors, because we would like to compute the, the integration answers rapidly. How can we compute rapidly? So if we consider our problems, the flow fractions is always parallel to the normal factor of the cross-section area. So we don't have the dot product here. So we only have the scalar. There is no factors. So the integrations, if we would like to focus the control surface 2 over v squared multiply the rho v dot dA. So we deal with these integrations individually. So and we assume the flow directions is always parallel to the normal factors of the cross-section area, and we can rewrite the equation to be the scalar items. But since we know that the v if not the uniform flow, so the integration problem is too complicated to deal with this integration along the control surface. So we define the alpha values here is equal to the ratios between this is the original integrations, and divided if we assume the velocity is the uniform flow distributions, and then we have another integrations, because the velocity is integrate uniforms. So we simply then change with a different cross-section area. So we can the velocity to be a constant value and take outside from the integration problems. So finally, we can very easy to build the integration for the bottom part. So the idea is since these items can be easy to compute, and we just simply multiply the correction factors alpha values, and then we can estimate the complicated integration on the left-hand side. So we already know that the situations for the laminar flow in a pipe, the alpha value usually is 2, because the velocity function is the parabolic. If your velocity field is the uniform flow, then we will have the alpha value is equal 1. And for fully developed turbulent flow in the pipe, and we know that the alpha is close to the 1 because the turbulent flow behavior usually would like to uh, change the velocity profile into the uniform flow. So that's why the two alpha values for the different condition, but the quality curves. Okay. So what are the ideas? The alpha, I just emphasize again, the alpha try to will be used to be the correction factors since we can compute these integrations value very easy because the velocity is uniform and we just take the velocity from flow be the constant, so we take outside and then multiply the correction factors to compute the original integration what we need. Okay, so the exercise just show one examples how to compute the alpha value by yourself. Since we know that this is the pipe flow and we know that the flow profile is the parabolic, and then how to compute the alpha value, and we already know the alpha is equal to 2. So first, we need to have the v mean velocity first, and as we know that the mean velocity is equal to the a over 1 and the integration of vr dA. So what is the a? This is for the pi flow, so the area is the pi real square, right? And what is the dA? And since we know that the dA is 2 pi r dr, right? So we just put the a and the dA go back to the equation, and then we try to compute the mean flow velocities. And so we just put the number here is a pi r equal square over 1, and we do the integration problems. Vr is the v max, and the inside is 1 minus the r divided r0 square, and there is the dA is 2 pi r dr, and because the domain is changed to the radial, so here we just have a radial integration from 0 to r0. So we just move some constant value outside. So we have the pi r0 square, and we have the b max, and the 2 pi outside. So the inside we only have a 0 to r zeros, and there is r minus r0 square and r cubic unit powers and dr. Okay, and then we just do the integrations of these problems. So the pi and the pi will cancel out here, and the upper only have 2 times of v maxima and r0 square here, and we do the integration. So here is r squared divided 2 minus R0 squared are 4 powers divided 4. Okay, and then the integration interval is from 0 to R0. So we just put the R0 inside the integrations. So there is 2 over R0 squared minus the 4 over R0 squared. So this is actually equal to the 2 over V maxima. So right now we know that the mean flow velocity in the pipe flow is 2 over V maxima. So we go back to see the definitions of alpha values. So the alpha is equal to A over 1 and the integration along the area, and the ratio is V divided the VR cubic hours here. So we actually know the V velocities function here, and we have know that the mean flow velocity is 2 over V maxima. So we replace the mean velocity by these numbers, and you just take a summarize and reorganize the equations. Finally, we have the equation 10 like the equation showing here. So you can see this is the integration unknown along the layers is too complicated. So right now we just make some new variable to replace the some parameters. So we find the u is equal to the 1 minus the r divided r0 square, and we compute the du dr values. So we know that it's minus 2 the r equals, and we also the r here inner items is equal to the r 0 over 1. So we know that there is a 2 minus 2 in the r0 square. So if we take a look here, there is r. So we just reorganize, and there is 0 here over 1. So based on this equation, we know that uh, the r, the r is equal to the EU and divided the 2 and move the minus 2 to the left hand side, and move the r0 square to the left hand side. So here is r0 square and the minus. Okay, so we can, and then take a look. First, the integration interval is start from the 0 to the r0. Since we change the domain to be a 2, so we know that the r equal to 0. So you see the u item here. The u is equal to 1, and if the r is equal to r0, then you put the number here. So this is u equal to 0. Okay, so we know that we can rewrite these items to be, we just keep the 16 here and the r0 square to square here. And the inside integration, the interval change to the 1 to the 0 because the condition here. And we have this parameter is a u qubit, have the u qubit, and we replace the rdr by the rdr and relation showing here. We have the minus r0 square, and we divided the 2 and the du. So this is, we can solve this problem very easy. So we just cancel out the r0 square, and there's 2, and this is 16, so it's a minus 8. So inside we only have the 1 to 0 U qubit powers and du. So this is a minus 8 and multiply the 4 over U 4 powers and from the 1 to 0. So finally we know that the alpha is equal to 2. So for many problems we can directly compute the alpha value by ourselves. And so if we already have the alpha values, we just we can easily to compute the complicated integration of the original velocity integration problems. So that is our equation 4. The idea is initially the integration problem for the velocities if not the uniform flow. So this item is too complicated to deal. And then if we have the alpha values already, and we can simply multiply the alpha by the integration for assumption of the uniform flow profiles, and then we can rapidly to compute the complicated integration showing the left hand side. So this is very important, and we know that based on the different flow conditions that alpha value will be changed. Okay, and where we showing here the alpha equal to 2 is a simple parameters for the condition is the flow velocity is the parabolic. Okay, so we go back to see right now. So we have the equation 3 and we have the equation 4. So we combine the equation 3 and the equation 4 together. So where we need to rewrite, as you see, before we put the equation 4 inside the equation 3, we just expand the parameters, uh, expand items along the integration of the control surface. And based on these problems, we assume this is a steady state flow. So which item we can move out? So we just take a look at steady flow. What are the meanings? A steady flow, that means the properties didn't change with the time. So if we take a look, there is a d dt. So and for the control volumes, because we assume our flow satisfy the steady state flow, so we can move out these items. And the velocity is always the normal to the control surface, so we don't have the part productions. So we move for the control volume, we only have the control surface items, and we know that the velocity always parallel to the normal factor of the cross-section areas. So there is no dot product. And then we can just assume the A2 area is our outlet, and the A1 is the cross-section area for our inlet. And we know that the outflow rate always minus the inflow rate. Okay, so we just expand this item for the control surface. So let's put the left hand side and right hand side, the sign are always the positive. So there is the minus, so we move to the right hand side, and there is the minus, so we move to the left hand side. And then we rewrite the equation. So we have the WP here, and there is the velocity items along the control surface. So we move out, and another integration along the cross-section area is the GZ1 plus the U1 and plus the P1 divided the rho. And the right hand side we have the turbine work rate and also the velocity items. And another is the elevations, the internal energies, and the pressures work. And we just move the Q on the right hand side. because this is usually we use the to be the heat dissipations, so use the minus here. Okay, so right now start from these equations and move to the next. We apply the equation for here. We know that the alpha 1, and then this is the integrations assume the flow velocity is uniform flows. And then right hand side is also use the alpha 2. Why we use the alpha 1 and alpha 2? Because the different cross-section area may have the different flow conditions. So the correction factor will be changed, not always the same, right? If the flow condition is the same, so the alpha 1 will equal to the alpha 2. And if you look at the inside for the integrations, there is a low VBA. And we know that the VBA is the discharge. If the discharge multiply the densities, and then we have the mass flow rate, right? And that is based on the idea the law is then change with the different spatials. So that means I will assume the flow condition is incompressible flow. Okay, so we can rewrite the equations. We don't need to have the integration operator because we know that this is the integrations is equal to the mass flow rate. So we rewrite the equations here, and we provide additional velocity for the low BA, so we only have V squared in here, and there is the mass flow rate. And for this item, we have the mass flow rate, and the inside is the energy per unit mass. And this is the pump, and there is a turbine. Since we tell you the pump will provide the energy, additional energy to the fluid systems, the turbine will out of the energies for the systems. So then there's a mass flow rate again, and we have a velocity square, and finally we have minus the heat energies. Because the energy for the heat always dissipate the systems. And for this equation, we totally divided the average G. So you can see the equation showing here is our final equation 5. So we go to the next. If we have the equation 5 and we define the pump head HP, this is the HP, and we define the the turbine head. In this item, this is the HT, and we define the head loss HL in here is equal to this item. So that the meanings is the internal changes and the minus the heat transfers. Okay, and so we know that the heat loss is related to the fluid problem is related to the thermal energy related to the viscosity actions. Okay, it's similar to we know that in the solid mechanisms, we know that the frictional force will generate the heat energies dissipations. So for the fluid problem, all of the frictional properties is related to the viscosity effect. So actually, the energy to western the thermal energy through the viscous actions. So we can also summarize our final equations 6. This is our energies equations for these chapters. Okay, so actually we have the the head, pump head. This is similar to the Bernoulli equations. We have a pressure head, elevation head, and the velocity head. And the right hand side we have the pump, the turbine head, and the pressure, elevation, velocity, and the head rows. So sorry, today we need to finish the chapter 7, so I go quickly and I already write down all of the equations we need in the slide. There's a difference for the previous class. I also write by my hand, so I teach the class by the handwritings. But because of the time limit, so I just already put all of the equation we need and in the slide. So if you catch out and fully understand what I mean for the previous slide, but only one important equation you need to keep in mind after these chapters is the equation 6. We call that is the energy equations showing here. Okay, and this is quite easy to remember because the formula of the equation 6 is quite similar to the Bernoulli equations. The only some difference is we need to have the correction factors for the kinematic items, and we have the HP, pump, turbine, and the head rows. The 3 parameters difference compared to the Bernoulli equations. So what are the physical meanings? We just derive our problems based on the curve systems, and we know that all of the energy can be interactions along the boundary only. And usually we know that we have the head, so we can compute the work very quickly. Is equal to the mgh, right? And there h here is the head energy head. And we know that the powers we need to divide it the certain time intervals. So if the question requires you to answer the powers, so it's very easy to compute the power by the m rate and the gh. And it's also equal to the gamma qh. The gamma is the specific weight, and this is a pulsar discharge. Okay, so specific gravities. Okay, so now the table just summarized for the energies equations. So I would like to emphasize for these tables is the major assumptions for the energy equations. Here, if we write the energy equation by these formulas. So the first is we assume the steady state flow. So there is no energies accumulation in control volumes. So we cancel out the integrations along the control volumes. And for this equation, we only have the one inlet and the one outlet. Okay, that's why we use the alpha 1 and the alpha 2. The 1 is the inlet cross-section area, and the 2 is outlet. And we assume the flow directions is parallel to the control surface factors, normal factors. Okay, and the constant, the temperatures for our problem is always the constant. This is based on if we have the constant temperature in the closed systems, try to satisfy the first laws of the thermodynamic. The energy is conservation. And there is just to summarize the different alpha correction factors related to the different conditions. So for the turbulent flow and the nozzles problems or uniform flow problems, we always use alpha equal to 1. And for the nominal flows in a round pipe, we use the alpha is the 2. Okay, and the 3 energy head is the pump head, turbine head, and the head rolls for our problems. Okay, so I think the material is I go to teach the material too fast, so it's a little bit too complicated. But right now, you just keep in mind for the energy equation shown in the table here, and there are many assumptions you need to understand. If your problem not satisfy the major assumptions shown here, so in that case, you cannot use the energy equation formula shown here. You need to go back to the initial energy equations definitions. Okay, that the equations I showing here still have the integration items. Okay, so maybe the time is the time to 10 minutes break. So after the 10 minutes break, we will do more exercise, and then in that way you will uh, figure out the key concept for our energy equations. Okay, so we stop here, and